Hi students, today's concept is Michelson Interferometer. This is the real instrumental picture of Michelson Interferometer. Now, what is Michelson Interferometer? The amplitude of light beam from an extended source, S, which is divided into two parts of equal intensities by partial reflection and refraction. These beams are sent into two parts which are perpendicular to each other and are brought together after the reflection from the plane mirrors M1 and M2 produce interference pattern which is in the form of circular order. Next, we have to see the construction. The main optical path, which consists of two highly polished silvered plane mirrors M1 and M2 and two parallel glass plates G1 and G2 of a same thickness. G1 plate is half silvered at backside so that incident beam is divided into reflected as well as transmitted beam of equal intensities. The two plates held parallel to each other and inclined at an 45 degree to the mirrors, and the M1 and M2 which are mutually perpendicular to each other. This is what construction. Next one, the working of Michelson interferometer. The light source coming from the S produces a parallel beam of a light when it passing from the source, passing from the lens L, and which is made to fall on the G1 plate. It is partly reflected at back surface of a G1 along AC and partly transmitted along AB. The ray AC is received by the plane mirror M2 so that it is reflected along the same path and which is emerges out along AC, AT. And the transmitted light AB is received by the mirror M1, the reflected along the same path and then moves along AT. After the reflection at back surface of a G1, thus two beams along AT produces a single source by the division of amplitude. These two beams are produces interference pattern under the suitable conditions. This is what working of the Michelson interferometer. Here we are using G1 and G2 two plates parallel. In this case, G2 is known as a compensating plate. Why we are using the compensating plate? It is used to equalize the reflected ray and transmitted ray. Light ray from the source suffering reflection at M2 traverses the glass plate twice time here. Next, but the reflected ray from the M1 traverses only once time. To compensate this one, for this exactly similar to the glass plate of a G2 parallel to G1 which having the same plate, same thickness, and the M1, M2 equidistances from the G1 and two paths are exactly equal. So we are using the compensating plate. See, this one is another one image of the Michelson interferometer. Here using the monochromatic light as a laser, two mirrors are perpendicular to each other and the beam splitter and the interference pattern which is formed on the screen. Next, circular fringes. The circular rings are produced with monochromatic light M1 and M2 which are exactly perpendicular. The several reflections takes place in interferometer. When the interferometer is in normal adjustment, the image M2 dash of M2, the glass G1 parallel to M2. The source S gives two virtual images, those are S1 in M1 and S2 is in M2 dash respectively. The D is the separation between the M2 and M1 and M2 dash. Then 2D is the separation between S1 and S2 which are coming from the source S. The light waves from the lens L after the reflection from M1 and M2 at an angle theta appears as if these have originated from the S1 and S2. Hence the two reflected waves towards I which are coherent, these two S1 and S2, the ray coming from S1 and S2 which are coherent and parallel, and they produce the interference pattern towards the I. And now we have to see, that is the separation D is between the M2 dash and M1, and the separation 2D is S1 and S2. Now we have to calculate the path difference which is coming from the S1 and S2. This one is path difference, that is S1K. We have to calculate. The angle theta is appears here. We using cos theta is equal to adjacent divided by hypotenuse. What is adjacent? S1 into K. Hypotenuse is S1 into S2. What is S1K? S1K is equal to S1 S2 into cos theta. We can see in the next slide, that one is by using the Pythagoras Theorem, the triangle S1 S2K. The cos theta is equal to S1K divided by S2 S1 into S2. The S1K is equal to what? S1 S2 cos theta. S1 S2 is 2D cos theta. Next, one ray coming from the denser medium, that is lambda by 2, then we get the 2D cos theta minus lambda by 2, which is the path difference. The condition for bright fringes constructive 2D cos theta minus lambda by 2 is equal to n lambda, then we'll get 2D cos theta is equal to n lambda plus lambda by 2, which is, we can write it as 2n plus 1 lambda by 2. The condition for dark fringes 2D cos theta minus lambda by 2 is equal to 2n minus 1 lambda by 2. We can also write it as 2D cos theta is equal to n lambda. Now you can see that is if the separation D is equal to 0, there is no air film, the whole pattern becomes dark. You can see that is D is equal to 0, the fringe pattern becomes whole, that is the dark. If the increasing the separation, that is D is equal to lambda by 4, the pattern becomes, the middle one is dark, next one is bright, like that. Next, D is equal to lambda by 2, the pattern becomes, one is dark, another one is bright, and another one is dark. The next, D is equal to lambda, then the pattern becomes dark, bright, dark, bright, and dark. This shows that if the separation is increases, then the radius of the fringes will be decreases. If the separation is increases, the more number of concentric rings will be formed. That's why the radius of the fringes will be decreases. That is, equation is given by Rn is equal to capital D square root of n lambda divided by small d. Then n is order of fringes, R is radius of fringes, capital D is distance of telescope, small d is separation between the mirrors. This is what the circular rings. The next one is, see the localized fringes and straight fringes. The shape of the fringes are observed for various values of the path differences. The fringes are straight when M1 is intersect with the M2 dash in the middle, exactly in the middle. In other two positions here, the shape of the fringes are curved and are always convex towards the thin edge of the wedge. This type of fringes are not observed for a long path differences. Next one, we have to calculate the wavelength of monochromatic light by using Michelson Interferometer. See, using the Michelson Interferometer, the wavelength of light from the monochromatic source can be determined. If M1 is moved forward or backward, the circular fringes appears or disappears at the center. The mirror is moved through a known distance d, small d, and the number of fringes n appearing or disappearing at the center is counted. For one fringe to appear or disappear, the mirror must be moved through a distance lambda by 2. Knowing this, we can write it as small d is equal to n lambda divided by 2. So the wavelength of monochromatic light is given by lambda is equal to 2d divided by capital N. This is what the calculation of wavelength of monochromatic light. Now we can see the applications of Michelson Interferometer. The first application is what? The Michelson-Morley experiment is the best known application for Michelson Interferometer. And also they are used for the detection of gravitational waves. And the Michelson interferometers are widely used in astronomical interferometry. These are the application of Michelson Interferometer. Thank you, students.